Hello everyone. This is our last session for this course of 3D bioprinting. So, what I'll do, I'll like briefly summarize the four techniques that we have studied so far. Okay, and as we are going over briefly over the techniques, I have prepared some questions, some easy questions that I want you guys to try and answer during the session. Like we can have detailed discussion on the question, as well as if you have any doubt related to that particular technique, you are welcome to share that doubt with us. And yeah, so that's how we will wrap up today. Okay. So, briefly, if you remember, we studied the definition of 3D bioprinting. So, it means that we are using additive manufacturing. It's an automated process to deposit a bio ink. Bio ink is basically a mixture of living organisms like cell or protein or anything derived from living organisms mixed with the biomaterial. Okay, or biomaterial can be absent as well. So that's the starting material for bioprinting that is deposited in a layer by layer fashion, okay, to generate a 2D or a 3D structure. So that structure can be used for either tissue engineering or for regenerative medicine or for drug screening or even for fundamental biology studies. You can use it. So here we are basically like automating the process of making tissue-like structure using 3D bioprinting. Okay, so and that's why it's a very important tool for the tissue engineers. If you recall, we have already discussed how to bioprint, right? We have already discussed during our initial classes. So during that class, we discussed what are the steps that one needs to follow. Okay, in ultimately to get a bioprinted tissue. So, can you guys tell me the first step that one needs to do in order to bioprint?
We need to come up with the sketch model.
Yeah, yeah. So we need to basically design CAD, right? Generate a CAD file. So you can either take medical images like CT scan or let me switch on my camera. So you can either use a medical images like CT scan or MRI images and then render it into a 3D model, or you can start with the 3D file of your own choice, okay? But you need to generate a 3D file, that too in .stl format. Then what's the next step that you would do?
Bioink preparation, ma'am.
Yes, you're correct. We need to prepare the bioink. So depending on what type of bioprinter you have, the properties of the bioink will differ. So accordingly, you will have to choose the material. And also, depending on what is your tissue of interest, you will choose the cell type and other bioactive factors in order to prepare this bioink. What's next?
Selection of technique which we are going to use, like which type of 3D bioprinting we will use.
So, like that should be like understood, right? So, like that would be like zeroth step. You already have a bioprinter with you. You don't
Some
need to.
post-processing.
So post processing, first you need to print, right? Post processing would be the last step.
And after that, the material which we are doing is converted into functional. Yes, that's yes, sir.
Sorry, I can you repeat? Your voice got very low. Can you repeat?
No, ma'am. After producing it, we have to check its compatibility. how the material is.
Okay. So your so viability you will check and all, right? But
Yes,
before that, how will you ensure that the ink that you made for the bioprinter, okay, that is basically working well? How will you ensure? So that's why there should be a third step here where you will uh, do optimization of parameters, right? You will try to check different concentrations of bioink and as well as check how those concentrations of bioink work well with different parameters of the bioprinter itself. So depending on what type of bioprinter, your parameters will differ. Like if it's extrusion, you will work with different pressures, different nozzle size, um, different flow rates, right? If temperatures can also play a different role. So optimization of parameters, that you have to do in order to select out the best set of parameters that you can use to print this bioink, and that gives good printability results. Means whatever CAD file that you have put in the machine, your ultimate objective should be that your final structure should look like that CAD file. It should not look anything other than that. Yeah. Then fourth step is basically you will do the bioprinting process. And the last step, as one of you said, is post processing. You can either do assays with it, like you can check the cell viability and all, or you can use bioreactors, or in small scale you can use petri dishes, etc., to actually do the maturation of the tissue and then use it for your application. So these are some steps, these 5 steps that one needs to do in order to ultimately get a bioprinted tissue model that they can use for some other application. Okay. So the first step is CAD modeling, right? So what all softwares that you can use to do this? Can you name some?
AutoCAD, Precision,
Yeah,
Precision,
yeah,
FreeCAD,
yeah. Yes, this is the software that we worked with. But what all others are there? Can you name some alternatives?
and FreeCAD,
Uh, can you say again? Sorry, can you say again?
FreeCAD,
S- Streaked? Sorry.
uh,
Um,
FreeCAD one software is
free CAD. Are you saying
uh,
free CAD? Oh,
FreeCAD.
oh, okay. Okay, fine. I haven't used their software, but if you're saying that, so there must be. Um, did I write it correctly? Can you tell me more about this software? I'm like hearing about it for the first time. Can you tell me more about it?
My bad. It's same like Fusion 360 and it's freely available without data subscription. That is the advantage.
Okay, okay, good. So
I
it's an open
started my,
source one.
yeah,
Okay.
when I started to do CAD modeling, I started with FreeCAD
Oh, nice,
to
nice.
generate
Okay.
SPE files.
Mhm. Great, great. It's good information that I got to know. Anyone else would like to contribute to this list? Yes, there is Katia as well. Then Blender, you can use Blender as well to create CAD files. So like Blender and FreeCAD, they are open source. You can use Tinkercad as well. These are also open source. So in suppose you don't have um like the pro version for Fusion 360 or CATIA, you can use open source ones. Okay, to do the CAD modeling. But the CAD file, every software will generate a CAD file in its own format. All these formats must be exported to .stl file for 3D printing. Okay, that's the important thing to keep in mind before you start the 3D printing process. Okay, so coming to the first type of 3D printing, 3D bioprinting technique that we studied is the extrusion one. Here, the concept is very easy to understand. What we do, we basically load the bioink into a syringe. That syringe is connected to a fine tip nozzle or a needle, and we then apply some pressure from top. Is called the extrusion pressure, because of which the bioink comes out as form of filament. Okay, and depending on how the pressure is applied, you can categorize the extrusion mode into again three types. So if you're applying air pressure, then the pneumatic extrusion is happening. Okay, that system is much more popular in the bioprinters that are commercially available. The pneumatic one is more popular. But if your material is very viscous, okay, and it needs very high pressure for extrusion, then you can use mechanical systems like piston or a screw for the material to get extruded from the needle tip. Okay, and when you start thinking about designing bio inks for the extrusion 3D printing, so here you need to make sure that the bio ink should be shear thinning in nature. So what's shear thinning? Shear thinning is those is a type of non-Newtonian fluid where the viscosity of the material decreases as we apply more shear forces at it. Okay, and as soon as we remove the shear force, the viscosity is increased. So with increase in shear, it becomes thinner. The viscosity becomes low. So because of which it flows easily. But when the shear is removed, viscosity is becoming high. So the flowable capacity reduces. So it's an important property for the bioinks for this bioprinter, because we want the bioink to be in a non-flowing condition inside the cartridge. Okay, and when we apply pressure, we want the bioink to transition into a much more flowing condition so that it flows smoothly through the tip of the needle. Okay, and in form of filaments, and like it forms filaments very smoothly on the substrate without breaking and give the desired pattern. But we also want that the material that is deposited on the substrate, it should not, the structure should not distort. Okay, so that is why we want the material to again regain its uh, like high viscous state. It should not flow anymore. Okay, if it starts flowing on the substrate, then the structure that we printed will get distorted. So if the material is shear thinning, we can expect this kind of behavior for the bioink to display. Okay, so these materials generally show good printability as well. Means whatever CAD file that you supplied, the structure looks similar to that. And shear thinning also helps in shielding the cells or any biological components from the shear stresses. All right, and we should make sure the bioink composition is made in such a way that the shear thinning capabilities will optimized, and printing is very good in that as well. So what kind of bioinks that you can work with that are available for extrusion 3D bioprinting? You can make a bioink with one component. All right, where there is only one biomaterial mixed with cells. Now, usually, if it's one component, then you have to like do maybe post printing processing, to make the structure more rigid. So here you can use UV light and the bioink can be made up of some photocross linkable material, or you can use alginate, suppose, all right. But alginate is not very shear thinning, so you have to make the constant composition bit shear thinning. So that's a bit more tricky, but you can do that by partially cross-linking it. And then complete cross-linking can happen after the printing is done by exposing it to a bath of calcium chloride solution and all. Okay. So you can also use decellularized ECM matrices. So basically, the decellularized ECM is obtained from tissues, animal or human tissue, where the cells are removed. So those are also shear thinning in nature, and those are single component. But again, cross-linking has to be done. A mechanism of cross-linking has to be done in that way as well. Or you can use enzymatic cross-linking step to retain the final structure. Here, the bioink is mixed with some enzyme like HRP, something like that, and the substrate for HRP is within the polymer matrix. So when the printing is over, you give some stimuli for the reaction to begin, and then the structure will be solidified. You can use ionic and covalent types, like both ionic and covalent, both forces to play an important role for the final structure to remain as it is. So you can use two polymers. Let's say sodium alginate is one that cross-links in the presence of calcium chloride ions. Another polymer can be, let's say, gelatin that cross-links in presence of some chemicals, all right, and the cross-linking happens in covalent fashion. So you can mix both of them and then gives the ions and the chemicals for the cross-linking to complete, all right. Or you can use supramolecular guest host interaction. Here, basically, the polymer chain is modified to contain some chemical molecules, uh, which shows this guest host interaction. And this type of interaction is physical in nature, all right. It's a physical cross-linking method, and it depends on the configuration of the guest molecule and the host molecule. So the guest molecule contains like proper configuration that fits well with the host molecule, and because of which this kind of crosslinks form between among the polymer chains, all right. You can use nanoparticle and polymer combinations as well. Here, the nanoparticle can contain some functional groups, or they can be electrostatically charged, right? Or like any non like van der Waals forces or something like that, that can basically hold together the polymer chains. All right. Addition of nanoparticle can also increase the shear thinning capability of the bioink. You can also use multiple polymers in the system of your in your bioink, but it's possible that um, you are only adding more and more polymers to increase the shear thinning property. But more polymer content is not good for cell growth. So you can add a sacrificial material that during the printing increases shear thinning nature. But once printing is over, you dissolve out the excess material that you don't want anymore, all right, and then let the structure grow in presence of cells, all right. So when you remove the secondary material that you added for increasing the shear thinning property, that will be like dissolved out and create pores inside your 3D structure. And that's good. That pores are good for nutrient and oxygen diffusion within the structure, and cells will grow better, right? Or you can just make a bioink composed of gels only. right? Microgels. So you can first cross-link a hydrogel, then do some sonication, or mechanically you grind it through some blades, sharp blades, in order to create microgels, means gel pieces which are of very small size, like in micron sized gel pieces. And that complete mixture of just cut up gel can be used as a bio ink. Here what happens, as they are like very tightly packed within a cartridge, it creates some irregular pores within the gels. So that's again is very good for cell growth, because they act as a passage for the nutrient and the oxygen diffusion, and also the cells can migrate well. It also becomes this system, this jammed microgel system is also a very good shear thinning material, all right? So it will show better printability as well. So these are some almost 7 ways by which you can think to start making a bio ink for extrusion based 3D bioprinting. Ultimately, the choice of the material depends on what type of bioprinter you have, first of all, and what kind of tissue you are going to target. So, accordingly, the material will be chosen, and optimization, parameter optimization, etc., will be done for the printing process. Okay. Before we go into this question, do you guys have any queries that you would like to bring to my attention? Any questions? Anyone?
No, ma'am.
No?
No, ma'am.
Okay. Okay. Others are also fine, right?
Yes, one more.
Yeah, okay. So this is the question that is there in front of you. The questions ask you, is it possible to make blood vessel-like channels using extrusion-based 3D bioprinting? If yes, how?
Ma'am, by using coaxial bioprinting, maybe we can make this type of structure.
Yeah, yeah, you can. So can you explain how can you use it, like so that others will also learn more about it?
It has two channels through which two different types of bioprinting material can be extruded, and that will be managed, or that will be taken under consideration by the software which we are using, and we can make the vessel in coaxial manner so that we can get this blood vessel like channels.
So in coaxial needle, there is a core and a shell, right? So in order to make a hollow blood vessel like channel, uh, like what will be in the core and what will be in the shell?
Ma'am, you mean what type of cells will be there in the core, inside and outside?
So again, I'm repeating my question. So yes, you can use coaxial bioprinting. Okay. So in coaxial bioprinting, we use coaxial needles. All right. Which are concentric like this. This is called shell and this is the core. All right. And you need to make blood vessel like channel, which is basically hollow inside. And since you can float two types of biomaterials, right? One will be from core, one will be from shell. So can you tell me what type of biomaterial should be there in the shell and what type of biomaterial should be there in the core in order to get a blood vessel like channel which is hollow inside? Take reference from all the type of biomaterials. You can explain with an example. We have discussed so many biomaterials that are used for making bioinks. Give an example from those list, which two combination of biomaterial can be used to create a hollow channel using coaxial bioprinting. Did you understand the question that I'm asking you?
Yes, ma'am. Yes, ma'am.
Yeah, okay.
We need to use some elastic property containing biomaterial.
Like, name one.
Ma'am, is the meeting should be very specific or
Yes?
the process of it.
Yeah.
Ma'am, is the material should be more specific or is it, for example, gelatin or engineering, the cross-link?
Okay, you can,
Yes,
yes, you can use, yes, for, extrusion-based bioprinting, gelatin and alginates are used, all right? And alginates are used. Now tell me, how will you, flow gelatin and alginate in this shell core configuration in order to get a hollow structure? You know the property of gelatin, right? Gelatin is a protein.
yes,
It, yes, it basically
ma'am, for
is
the
in.
formation of inner that hollow surface, we can use gelatin.
Mhm. So you will
We,
flow gelatin in core or in shell?
no, that way, that's just, I'm saying, I just asked whether the material we can.
Ma'am, as I can
Because
remember,
I,
there was a material which was used, first we use them and then uh, it will dissolve. I didn't remember its name, but it was something that we use to create hollow structure. Like it is solid, and after dissolving it, it get removed. I didn't remember its name. Can you please recall it?
Do you, I think we studied it. Is it PEO, polyethylene oxide?
Yes, ma'am. I don't remember it, but you have told us that it was the material that we use, and after that, if we want to create hole in something, and
Mhm.
it get dissolved, if we want to create a hole, I'll go
Right.
through the chapter. I didn't remember it right now,
It's
ma'am.
fine. It's fine. Let's focus on the two materials that is like uttered, right? Gelatin and alginate. You can use both gelatin and alginate for this application. So gelatin, you know the property of gelatin, right? So it solidifies at low temperature, and when it is heated, is in heating condition, it will form liquid. Whereas alginate cross-links in presence of calcium chloride ion. So now user engineering brains in order to decide in which section of this coaxial needle will you flow gelatin and alginate in order to get a hollow structure.
Ma'am, can you repeat the question?
The question is these two materials, right? Gelatin and alginate, all right? These two materials are there with us, and now you want to make a coaxial, you want to make a hollow channel using coaxial bioprinting using a coaxial needle, all right? So now my question is, in which section gelatin will flow in the needle, and in which section alginate will flow in this needle in order to get a hollow structure? How will you flow these two material in a coaxial needle in order to get a hollow structure? Will gelatin be flowed in core or shell? Similarly, will alginate be flown in core or shell? You know the properties of gelatin and alginate both. Gelatin basically is solid at low temperature, less than 37 degrees Celsius, it's going to be solid. But if you increase the temperature to 37 degrees Celsius, it will start becoming liquid. It will flow out. Whereas alginate, it cross-links in presence of calcium chloride ion, and it will stay as it is as long
Ma'am,
as
gelatin
calcium.
will be in core
Mm-hmm. Yeah, go ahead,
and
please.
alginate will be in shell. Because ma'am,
You are correct. What you guessed, you are correct. But tell me the logic. Why did you come up with this? And also in this configuration, when gelatin is in the core and alginate is in the shell, in this configuration, how will you cross-link alginate?
ma'am, alginate is, it's more stable than gelatin, and it is more mechanically, like it can tolerate more stress. That is why it will be used as a shell material. Whereas gelatin has lower viscosity,
Yes, that
so
you're
it will
correct.
be in core.
Yes, you're correct. But again, it is much more rigid. Alginate is much more rigid after it is cross-linked. So how will you cross-link the alginate that is flowing inside the shell so that you get a stable hollow structure? From where the calcium chloride ions will come in this configuration? You got my question?
Yes, ma'am. Ma'am, so you are asking that how this will be crossed using calcium ions, because we used
Yes.
calcium as a cross-linking agent. No,
Yes, yes. How will you supply calcium ions in this configuration?
maybe we can supply between the two, like the two needles. There will be something that will provide calcium. I don't know, ma'am.
So if we do that, then we will use a triaxial needle. There will be three channels in the needle. So there are only so in that is not we have. So what you can do is very simple. You can just prepare gelatin solution, all right? Um, Rather than using water to prepare it, you can use calcium chloride solution, like, or you can mix some volume of calcium chloride solution with gelatin, because gelatin won't get affected with calcium chloride at all, but you are going to supply some calcium chloride ions, or sorry, calcium ions in the core, right? So the core will have both gelatin and calcium chloride solution. And when alginate is flown in presence of this core material, it will get cross-linked. All right. Or you can form this type of alginate hollow structures in presence of a core solution of only calcium chloride. You don't need gelatin at all for that. You just need to make sure that the flow rate of calcium chloride solution and alginate, they are synchronized well. All right. Um, one should not run faster than the other. Otherwise, hollow structure won't be made. So, got it?
Yes, ma'am.
Okay. There's another way, uh, another variation of extrusion-based 3D bioprinting that can help you make blood vessel-like channels. That is called sacrificial and free-form 3D bioprinting. Here, what we do, we create a support bath of some biomaterial, okay, whose rheological properties are defined. And then you prepare a bio ink from the same biomaterial of this as the support or a different biomaterial. But the rheological properties, that is shear thinning, both of these materials should be shear thinning in nature. And what you do, you basically um, immerse the tip of the needle inside the support bath, and as this needle moves in order to make the 3D file, a 3D model, your ink gets deposited inside the support bath. Now, the support bath can be cross-linked, all right? And the ink that to deposit, it can be washed out to create a hollow structure inside the support bath. Or what you can do, you can wash out the support bath and keep the bioprinter structure that you made with another material intact. So in uh, both way of doing can help you create like channel like structures. Okay, made sense? Do you remember this uh topic that we discussed earlier?
Yes, ma'am.
Yes. Yeah. Okay. So using these two variations of extrusion-based 3D bioprinting, you can make blood vessel-like channels, which are quite complicated. It's but to make it by itself. Now we also discussed about droplet-based bioprinting. So basically, we use droplets as the unit structure to make a 3D structure out of it. And each of these drops have like a very in a deposited in a very controlled manner. Means we know the volume of each drop, and they are very precisely arranged in 3D structure to on in order to get a 3D model. There are various advantages to it. First, it is simple. The technology to make drops is very well established, so the entire process is very simple. It is very versatile, so you have um more options of material available to make bio ink for this type of technique. Even you can just use water based material like cell culture media and all, like in order to create drops you need low viscous materials, so that makes the technique very versatile, and you have very great control over how the pattern is made. All right. So there are some types of droplet-based bioprinting that we discussed. There is continuous inkjet, means continuously the drops are coming out from the tip of the needle. Then there is drop on demand, where the drop is created only when it is needed, so that it saves your bio ink volume. In continuous inkjet, there can be a lot of wastage of your bio ink. But how the drop on demand is done, that mechanism differs. Like you can use heating coils in order to create droplets, that is thermal DOD, or you can use piezoelectric actuators, which basically changes its shape in presence of an electric field, and then deformation of the cartridge basically generates a droplet. Or you can use pressure plates that moves from its position in presence of electric field, that transiently increases or decreases the volume of the bio ink inside the cartridge, and that basically helps in generation of droplet. All right. So all these four of these techniques, they're all inject, means there is a needle needed for generation of droplet. Then in under inkjet, there is another technique, that is electrodynamic jet bioprinting. Here, droplet is generated in presence of electric field. So you apply opposite fields. One, let's say at the tip there is a positive electrode, and at the substrate there is a negative electrode. And as you apply the voltage, the surface tension is overcome, and then the droplet is generated. So here you have much more greater control over the range of the droplets that you can create. Then you can use systems that does not use a needle or nozzle. All right. So one example of that is using acoustic bioprinting technique, where you use golden rings which are arranged in concentric pattern. All right. And there is some piezoelectric actuator as well, like a substrate or something like that, which changes its shape, and that basically causes the gold ring to vibrate, all right, and create sound wave. That sound wave propagates within the bioink reservoir, and the sound waves that are created, they are circular in nature, where the center of this circular sound wave pattern consists of high energy. This energy basically travels through the bioink reservoir, and a droplet gets ejected from the center of the reservoir. So this technique is very good if you are using cells or bioactive factors which are sensitive to shear stress or heat or pressure, or like like any type of environmental condition that is very harsh, that are there, like electric field can also kill cells. So you, if you want to circumvent all those stress factors, then this is a very better technique. That's a much better technique. Okay. But here there is much more restriction on what type of bio ink material can be used, because if we use a very high viscous one, then the sound wave will not propagate well. So that needs to be taken care of. You can also use a microvalve system in order to create droplets for bioprinting. Here, the microvalve is connected to some electric field and magnetic field stuff that basically helps in movement of the plunger that is connected to this microvalve. So as the plunger moves up, the tip of the cartridge, it becomes open for bioink ejection. As the plunger is moves down, it basically blocks. So you can use in this case bit more viscous solutions as well. But the resolution of the bioprinting, it becomes less. Like the droplets that you will get, they will be a bit more large in size, like 100 microns or more. So these are all different types of bioprinting, droplets with bioprinting methods that we looked at. And there are some materials that are very widely used, like alginate, collagen, methacrylated gelatin, PEG or PEGDA types materials. Each of them has their advantages and disadvantages depending on what is your tissue type, and what is available to you as well, what is cost effective for your project, you will choose your material and do the bioprinting. Now, can you name a biomaterial which is most commonly used for droplet-based bioprinting? And also explain how can you make a 3D structure using droplets using this biomaterial? Is my question clear to you?
Yes, ma'am.
Yes.
Go ahead, give it a try. So these are some of the materials that are used for extrusion-based bioprinting. But we already discussed a paper as well, where in that paper they used one of these. So that's the basically answer. If you remember, you can.
Methacrylated gelatin.
Okay, okay, fine. But actually, alginate is most frequently used. That's fine. Methacrylated gelatin can also be used. It's totally fine. Now, can you explain how can you do uh, droplet-based bioprinting with methacrylated gelatin to create a 3D structure? Yes. So, and alginate also very commonly used for this droplet-based bioprinting. Now, tell me for either material, if you're using either of this material to create a 3D structure using droplet-based bioprinting, how will you proceed? How will your steps look like?
Ma'am, first we have to make the binding.
Okay.
That will be the initial step.
Okay. Can you repeat again?
Ma'am, first we have to prepare the solution for the binding.
Yes, yes. Your solution
Yeah.
is with you. Yeah, your solution is with you. You have optimized all the parameters and all. You see that your parameters work well and it is generating drops now. Okay.
Uh,
Now my question is, how will drops? How will you use these drops in order to create the 3D structure that you want using the droplet-based barbering technique? Whatever technique you have with you is totally fine. Don't worry about what type of, is it an inject or a acoustic and all. It doesn't matter. Just try to imagine you're doing the bioprinting. You have a substrate. There are drops. Okay, but
ma'am, we have
drops
to
themselves. Yeah.
ma'am, we have to make it as layers, drop by drop layers.
Yes. But how will you make sure that the drops can support, the first layer of drop can support the second layer of drop? How will you design the bioprinting process? You know the property of both of these materials, right?
Yes.
Yes.
Ma'am, should we harden the shape?
You should,
After the
yeah,
uh, actually once the structure is if we get the print, we have to make a separate solution for hardening for sure.
separate solution for again, come again.
No, ma'am. By drop, we have formed the layers of it. Then
Mm-hmm.
after that, we have to keep any separate solution for hardening or this one for the material to cross-link like that.
Yes, yes. So, for let's say that's true when you going to use material like alginate that can cross-link in presence of calcium chloride solution. So what you will do, you will deposit a layer of alginate droplets, then you will add a layer of calcium chloride solution droplets. You can either spray the calcium chloride in between or you can just add droplets. Give some few seconds, it will cross-link, and then you can deposit another layer of alginate droplets. But what about if you're using methylated gelatin? How will that process look like? If your bio ink consists of methylated gelatin,
I
yes,
think we'll follow the same, but I think that hardening part will differ. We have to use another which is alternate for it based on the material which we are taking.
yes. So the cross-linking method that you will use is basically light here.
UV.
UV, yes. So you will basically alternate between the material deposition and then UV light exposure and then material deposition and then UV light exposure because you want each layer to stand on its own and it should be able to handle the weight of the above layers, right? It should not collapse. So that is how you would do the bioprinting steps, okay, using drops in this way. All right. Okay. Then we looked at another type of bioprinting technique that is laser assisted bioprinting. Here we realize that we are going to work with drops again, but the way the drops are being made, that's very, very different from the earlier methods. So here we use laser either in the UV or IR range, and it falls on a structure that is called ribbon. Now, what is ribbon here? Ribbon consists of three parts. First part is the transparent support through which the light can pass through. The next layer is the laser absorbing layer. So it can absorb the excess energy of the laser. Okay, and as it does, it basically at molecular level, some molecules starts evaporating. And due to that evaporation step, a droplet of a droplet kind of a vapor bubble. Because of this evaporation, a vapor bubble starts forming at the absorbing layer. Below the absorbing layer, there is a thin layer of the bio ink. So depending on how big the vapor bubble is forming, then how thick is your bio ink layer directly in contact with the absorbing layer and the laser power as well. So all these factors will determine the size of the bio ink droplet that is going to be formed. Now here, if you are optimizing things very nicely, you can basically print one cell at a time. Means one droplet can have one cell only. Or you can create large droplets where more than one cell basically can get accommodated. And all these droplets gets fall all in on a substrate. So the printing step will also be affected how far the substrate is from the ribbon. The wettability of the substrate will also determine the morphology of the droplets that is going to be formed ultimately. Then another parameter that one needs to take care is the viscosity, surface tension, and the thickness of the bioink. If the bioink layer is very thick, then it's possible that the droplet may not form. Because here, for the formation of the droplet, what you're relying on? You're relying on the property of the absorbing layer and the formation of the vapor bubble and how big the vapor bubble is forming. So if the thick bioink layer is there and your vapor bubble that formed is very small, okay, then it's possible that enough energy won't be there in the vapor bubble to create the droplet. It's also possible that your vapor bubble is too big, all right? And we defined a parameter that's called gamma in our lecture. That gamma value, it should be within the two threshold values that determine uh, what's the regime of the droplet formation we are in. So as I was saying, if the vapor bubble size is too big, then you can cause spraying of the bio ink. Okay, so you won't get single drops there. The ideal scenario is you should get a jet of single droplets, a stream of single droplets that falls on the substrate. Okay, and because of which you get a 3D structure. Now, here control is much more. We are getting much more control over droplet formation than the droplet based techniques that we previously studied, because here we can actually pattern one cell at a time. Means that's the highest resolution that one can expect here. That makes the technique also very expensive because it has to use a laser source and laser sources are very expensive. Then the absorbing layer itself can be made up of very precious materials like gold, titanium, silver, and all. So the technique itself is very expensive. So now, I've already explained this, but I want you guys to answer, how is droplet formed in laser-based bioprinting? If you recall the process, let me know. How the laser ultimately leads to the formation of a droplet in this technique. If you have understood, then you can answer. If there is doubts, let me know.
Ma'am, I think in a given interval, the laser will be focused on the bio ink,
Mhm.
and by that, the bio ink will be forming droplet.
But how? How the laser is going to cause the droplet to form? What's happening in between the laser and the bio ink? Look at this
From the
diagram.
intensity of the intensity of the laser will create droplets, and they will be like drops will be formed by the help of the intensity of the light. We will alter the intensity to which the bond will be broken, and I can say the
So, see, you're missing the point, like the main point of why the
Ma'am, are you
droplet will
asking
form.
about that ribbon or how that material will absorb and
Yes, yes, I'm talking about the role of the
ma'am,
absorbing layer here, how the absorbing layer is acting in order to generate droplets.
ma'am, is it that the laser is focus at the ribbon at specific time, and
Mm-hmm.
the layer will be creating a bubble, and it will be receiving the substrate so that you get the drops one by one, the ribbon part.
Yes. Yeah. So the vapor bubble that get formed, so that vapor bubble gets formed because there is a absorbing layer. So the energy that the laser is giving, that energy basically alters the molecules, okay, molecular arrangement in this absorbing layer. It forms plasma, all right, that at a very, very, like, you cannot observe it with your naked eye, but uh, that plasma helps in formation of a vapor bubble. It's like element at that spot is evaporating, it's leaving its space, so it's creating a empty, a bubble like structure. And usually this bubble is very small in size. It's like size is almost negligible to the thickness of the bio ink. All right. Now, this vapor bubble that gets formed, it should be big enough so that it can overcome the, or it can reach, it should be big enough so that it can reach the free surface of this bio ink. Okay. So it should not be too small. The vapor bubble should not be too small that it cannot reach the free surface. In that case, no drops. It should not be too big that the size of the vapor bubble exceeds the thickness of the bio ink. If that happens, then the spraying can happen, but it should be in between. The size in should be in between so that it should be enough to overcome the surface tension of this layer of bio ink and then create droplets. So this sweet spot we have defined using a parameter called gamma, if you remember. That gamma was basically defined as H and R max. R max is the radius of this vapor bubble, the maximum radius of this vapor bubble, after which it will burst. Okay. So, and H is basically the distance or the gap between the center of the initial vapor bubble that forms immediately and the free surface of the bio ink. So H is basically variable. It's going to increase and increase until it reaches R max. So gamma can be like in two regimes that we already saw. So go back to that lecture. You have the recording and the PPT as well in order to understand more on how a laser is basically helping in formation of the droplet. If this discussion is not clear. Otherwise, if you have any doubts, let me know. Mhm. Any doubts from anyone? Did you guys understood how the laser is helping to create droplets here?
Yes,
Or
ma'am.
base?
Yes.
Yeah. Yeah. Okay. Like you should go back later if there is any doubts, because there you will understand much better how the gamma value is being used to in order to understand the regime of droplet formation and all. Okay, and also I have explained in much more detail there. Okay, if there is any doubt. Then lastly, we discussed about the fourth type of the bioprinting technique that is available right now, that is light-based VAT polymerization bioprinting. We discussed it on Saturday. Okay, so this technique basically relies on using a bath of bioresin. So here we use photo cross-linkable polymers as the bio ink. Okay, that is used in a bit large volume so that it can make a bath or a vat. And into this vat, we basically give patterned light doses. Okay, that causes chemical reaction or photo reactions to happen at some discrete points within the vat. So wherever the light touches the vat, the chemical reaction happens. So the liquid bioresin changes into solid hydrogel. And in this way, when we do it layer by layer or point by point or in the whole volume at once, we get a 3D or a 2D structure. Okay. So there were different modes of operations that we saw. Basically depends on how the light is being um, exposed to the vat. Depending on that, different modes are available. We saw there was two photon lithography where we use two lasers coming from two different directions, like from top and bottom. They meet at single point, and this point basically translates in XYZ direction within the vat. And wherever this point goes, the material gets cross-linked. So the way the point moves is called raster scanning, means the point moves like one row at a time. So if the XY plane is like a square that is say distributed in small squares again, then the point will move from square 1 in row 1, then square 2 in row 1, like this until all the squares in row 1 are covered. Then the point will move, translate to row 2, and then cover all the points in row 2. So in this way, the structure that was there in one plane will get formed. And then the laser will translate to the next planar plane, that is next Z plane. And in this way, in layer by layer fashion, the point is moving and creating the 3D structure inside the vat. So in order to get the 3D structure out of the vat, you just have to basically remove the uncross-linked resin, wash it out, and you will get the 3D structure. This is one way of doing this. Another way is you use a layer of light. Okay, you don't use a laser point, you use a planar layer of light. And this one layer of light, when it comes in contact with the resin, that layer gets cross-linked. And then due to the movement of the built platform and within the vat, another layer of bioresin gets exposed with the next layer of the CAD model, and accordingly it will get cross-linked. So in this way, you can do the printing process in a layer by layer fashion by using a single layer of light. Now, in this case, the light that is coming and falling on the vat, that is patterned. Okay, we use special type of mirrors here, and also we use digital mask that we discussed previously. What a digital mask, which basically allows light to come out as a way that the CAD model is. Okay, so some regions are dark in the pattern, so the light will not come out, and some regions are transparent. So as the light uh, like passes through the digital pattern, you get a pattern light. And that pattern light is shown on the transparent surface of the vat so that the resin gets cured only in that pattern. Okay, so this is called digital light processing based 3D bioprinting, DLP 3D bioprinting. Now, if you use light, um, a pattern light, if you use pattern light on a, let's say, rotating vat, so what happens as the vat is rotating, the pattern light is shown in all the directions, all right? So the structure gets formed, the structure gets solidified within the vat in within few seconds. So the entire structure gets made within few seconds. You don't have to um, do layer by layer here. That is called volumetric. So in this particular method, the volumetric method, you can use multiple light sources and keep the vat constant. Okay, so that way of volumetric bioprinting is also possible. So we discussed all these three techniques in more detail as well in the last class that was on Saturday. Those who were not there, recommend you to go through the notes and the recording as well. So now materials which are compatible, types of materials which are compatible with this type of bioprinting, it is mentioned here, right? So usually we need to use photo cross-linkable derivatives of any natural or synthetic material that you're using. Okay. Uh, if the material is not photo cross-linkable, if the solidification does not happen in response to light, then you cannot use it as easy as it, because here light is basically directly coming in contact with your biomaterial and um, causing the material to transition into a solid structure. So the material must respond to light. Now, the photochemical reactions can follow different mechanisms. So there can be functional groups that responds to, let's say, chain polymerization. There can be functional groups that responds to step growth polymerization, and there are many others. Okay, so each of these polymerization reactions has its advantages and disadvantages, and that will ultimately impact the final structure that you get. Apart from the polymer that you're using, in order to improve the resolution of your structure, we add some additives. So first additive that we must add is the photoinitiator, because in absence of photoinitiator, um, the reaction won't start at all. As the name says, initiators. So these molecules are added at a very, very low concentration in comparison to your hydrogen, because they release some toxic free radicals. So you don't want a lot of free radicals to be there in your bioink, because they can then damage your cells. You need only a little bit so that the reaction gets started and you do the cross-linking. That's it. Apart from these photoinitiators, people also use photoabsorbers. So what are photoabsorbers? They basically absorb the excess light that can penetrate within the hydrogel. So cells, they are transparent in nature and they can scatter light. So all of these scattered secondary light beams that can travel within the vat, it can basically cause unwanted cross-linking and then distort your 3D structure overall. So in order to limit that, or in order to prevent that, these photoabsorbers basically absorb the excess light. And another advantage is that they do not interfere with the photo cross-linking reaction. Also, they do not interfere with the cells as well. So they are kind of inert, and they are added only for the purpose of like limit light penetration, limit or absorb the unwanted light that has entered the vat. Okay. Now, if your photo cross-linking reaction is sensitive to oxygen presence, then you can add some scavengers or molecules, scavenger molecules in order to absorb the oxygen. This again helps in improving your structure resolution. Then you can also use some refractive index modifiers that basically improves the optical properties of your bioink. Then you can also add some nanocomposite components, okay, like silica, graphene. Again, they can either improve the optical properties, or they can uh, improve the biological properties of the bioink. Like, but the main two things that are added is the photoinitiator and the photoabsorbers. Okay. Then some special points that one needs to consider is like you need to understand how the bioink components are getting cross-linked. So usually photo cross-linking happens, but the material can also respond to other cross-linking methods like temperature. So for example, gelma, which is a derivative of gelatin. So gelma can cross-link also in presence of low temperature, means it can form gel in presence of low temperature. So you need to make sure that the printing temperature that you are using is above its gelling temperature, so that during the printing, gelma does not solidify. Okay. So we need to take care of those things as well. Okay. So if that's clear, again in more detail, if you want to know, lecture is already there, and you can go and refer to it later. If you have any questions, let me know. Otherwise, we will proceed with few more questions that I have. Any questions?
No, ma'am.
No? Okay. Uh, for those who didn't attend Saturday's class, if you guys have any questions. If you have already seen the lecture, recorded lecture, then it's fine. But if you haven't, if this topic is new to you,
No, ma'am, it's clear.
it's clear? Okay. So let's proceed with this question that is on your screen right now. Which of the following type of wet polymerization technique used pattern light for photocross linking and to create 3D structure? You have to select all that apply, means more than one option is correct here.
From first one and second one, A, B.
So B is correct. In A we use laser point. We don't use pattern light. Okay.
Okay, okay,
So A is not correct. Okay. So, but there is one more option that is
B is
correct.
also correct.
Ma'am, C.
Mm, no, C is not correct. C is again we use laser point. D is correct here. Okay. So in volumetric additive manufacturing, also called VAM, here also we use pattern light. By pattern light, I mean the light passes through a digital mask. So in digital mask, what happens? There are some dark regions, black regions through which light will not pass, and there are some light transparent regions. So when this light passes through this digital mask, what you will see, that light will come like this, means the light will only be present in these two transparent regions. So the 3D structure will be like this, that will get solidified in a layer. Got it? This is called pattern light. So that is used, this pattern light is used only for the technique B and D to create a 3D structure. Okay. Is the question. Arrange the following bioprinting techniques in ascending order based on their highest resolution. Okay. So these are some F, actually A, B, C, D, E, F. So these are some 6 techniques that we've already discussed in this course. We have to arrange these techniques based on their resolution. So highest resolution will come at the end, and technique with the lowest resolution will come in the beginning. So if you recall, you can answer it. If you recall what are those techniques are, what we discussed during when we were talking about them, the resolution part and all. You guys can answer them.
F and A will be coming in the beginning, ma'am. And then
So let me just draw a line. Okay. This line means here you will put the lowest resolution techniques, low resolution technique, the lowest ones, and here the highest resolution technique. Okay. So you just said A will be towards where?
lowest
Lowest one. So A will be towards lowest and
F.
F. F will be towards lowest. Okay, fine. What about others?
C will be in the most right direction, ma'am. Highest resolution.
Okay,
Second, next to C is D. That is thermal droplet.
so it will be towards the left of C or right of C?
Left of C, ma'am.
Left of C. Okay. What about B and D? B and E?
We can write it like B, D, and E, ma'am. B
So where
after F,
B
ma'am.
will come
After F, ma'am.
after F, we can write B here and E.
I think we are
Is
missing
it?
one.
No, all the 6 are written now.
That's it.
Okay. So let's see what's the answer. So here I have drawn a line like this, a line figure like this, okay, where 2000 micron is the lowest resolution, and 5 micron is the highest resolution. So, in this, if you
Ma'am, you
see
change
F,
the
Ma'am, are
slide.
you writing somewhere?
Just change the slide, ma'am.
oh, yeah, is it visible now?
Yes,
Yes,
ma'am.
ma'am.
Yeah. So I have drawn this kind of a number line, okay, a line figure where the rightmost part where 2000 is written is the lowest resolution that we can get, and 5 micron is the highest resolution of printing that we can get. Okay, so F, that is electroaerodynamic jetting, it spans this entire region. Means depending on the electric field that you create, the bioing properties, okay, the distance between the tip of the nozzle and the substrate, all this can, if you vary, you can generate droplets ranging from the size of 5 micron to 2000 micron. Okay, so F is basically can cover the entire range. Then A, that is extrusion based 3D power printing, the lowest that we can go is 100 micron. Then B, which is light assisted bioprinting. As I told you, we can print at the resolution of a single cell. Okay, so that is why we can actually do bioprinting or generate droplets in the range of 10 to 20 micron. So this is the range for B, resolution range for B. C, that is DLP, digital light processing bioprinting. It can also range, like it can also give you a big range of resolution, like from 10 to 50 micron. Okay, but again, it depends on your um, bioink properties, the machine type you're using, light wavelength, and etc. Like there are many properties that comes here, but in literature, people have reported the minimum of 10 to 50 micron for C or DLP bioprinting. Then D, that is thermal DOD. Here, people have reported the lowest size of the droplets to be around 30 to 50 micron, and whereas for E, it is basically for VAM. Here, the literature says that the lowest that you can go is 40 micron. So, in this way, we can arrange uh, these six techniques, okay, in order of what type of resolution it can work on. All right. Is it clear?
Yes, ma'am.
Mhm. This is the last question. Which bioprinting techniques utilize photocross-linkable hydrogels as a bioink component? Select all that apply. Means there is more than one option that is correct. Additionally, explain how the use of photocross-linkable hydrogels contributes to the formation of 3D structures in these techniques.
Ma'am, yes,
Yes, come again. A and
A, C.
A, A. Okay. So again, I'm asking, like, do you think C is correct? Do you need photocross linkable hydrogels for C?
I thought in a way that all the three methods which will use this one, because if you use a specific material which has photo cross linkable this one, so it might work. So I thought in that way.
So, like, I understand. So, in extrusion-based 3D power printing, yes, we can use photocross linkable material. Okay, we'll come to later, like how it helps in the formation 3D structures. We'll come to it later. But what about, like, there is one more answer that is correct here. C is not correct, by the way. It's either B or
Um,
D now.
and B,
D. Yeah. Did you understand why C is not correct?
no, no.
You don't know? Okay. So in
One
C,
doubt, ma'am. Actually, in laser, while we are doing,
mhm,
the ink which we are using, that time we can, laser is based on that observe how the droplet, how the substrate
yes,
comes out, ma'am. So
yes. Yeah.
why cannot we cannot use laser?
Why can't we use laser, or why can't we use photocross linkable material, you're
Yes,
saying?
ma'am. Yes, ma'am. Yeah.
See, um, people have used, like, means you don't generally need photocross linkable materials. Like, it's not a necessity. Okay, means you don't need exactly photocross linkable materials for laser, but I let me check. I think mm. So whatever literature that I've seen for this bioprinting technique, they have not used photocross linkable materials. They generally use alginate or any other synthetic polymer that is of good viscosity, because we don't want light to directly start the photocross-linking reaction while it is in the ribbon. You understood?
Okay, ma'am.
Means
Got it.
if the yeah, if the reaction starts in the ribbon itself, then the droplets won't form. It will like stick to the ribbon.
Yeah.
So, and also for electrohydrodynamic jetting, you can use photocross-linked materials, but again, it has to basically respond well in presence of electric field. So if it doesn't, then you can't use it. The necessity is again not there. But
Yeah, but
yeah, what?
no, but I thought in a way that generally the material which we use the first we use UV now for photo crossing. So that
Mhm.
I thought in that way. So I thought it could be possible.
Yeah, yeah. But for D, obviously it makes sense. In presence
It
of
makes
light,
more
only the
sense.
crossing.
Yeah.
And for extrusion also, if material is not photocross linkable, but it is shear thinning, it will work. But people use extrusion, photocross link material for extrusion because it helps in quick post curing step. So as soon as it falls on the substrate, you shine light and it will cure quickly. The same can be done for electrohydrodynamic jetting as well. Like, as soon as the droplet is formed on the surface, it should basically you shine light and it can. So now if I think about it, B is also correct. Like, you can use photocrosting of materials, but for C you should not. Like,
Okay.
it is not advisable because, as I said, the light will start reacting with the material and you won't get droplets. Okay. So for B part, additional, the next question that I'm asking, um, I think I pretty much summed up like why you need to and how the material is contributing to that technique. But yeah, we can skip it. So any questions? Like, I am done from my side. Like, Any questions from your side, like any topic that you want me to discuss today, or any question was not clear?
No more.
No doubts. Okay,
Yeah.
great. Okay, yeah. Others also same, no doubts,
No questions, ma'am.
no questions. Okay. So
Yes.
okay. So let me stop recording and like we can have a discussion.